anyone else has a question, quickly pop it in the chat. But otherwise, you are free to go about your day or night or afternoon.
Yeah, also add that for my apps, you can download the source code from the apps. So they have a tab that says source code, just go and download it. So I haven't advanced yet to using all of those GitHub things. So I just have just download the file that runs the app and it's there. So yeah, and it's in R, it's not in Python. And some people like Morgan would disagree with me, but I do think that R is better than Python.
Both is good.
Yeah.
Oh, Claire has a quick question, Michael, if you're there. Claire is there. Claire is there. But
hello. Yes.
Oh, yeah,
so it was great, absolutely great presentation. Really enjoyed it. But all your data were bulk rock data. I work in rare earth elements and things like zircon and garnet and in metamorphic rocks, which are completely different. Any hints for sort of, I can plug the data into your wonderful spreadsheet and get some numbers out, but then what do I do with them?
Well, that's an excellent question. I don't know yet because I haven't done it. The last time I did the metamorphic stuff was about 10 years ago. So I'm sorry I can't help you there. But yeah, the thing is just go insane. Maybe you will find stuff, maybe you will not find stuff. If you do find stuff and you don't know how to interpret it, send me an email and say, look, I garnet or whatever, and I have this. What does that mean? I don't know. I can think. And feel free to develop your own things. I mean, if you can kind of, it's an app that gives you numbers. And if you can find a way to do something useful with those numbers, go for it. Why not?
That's really useful.
Yeah. I think separating it into those two components, one is the parameterization, which then enables you to communicate with someone else and say, this is my profile, and they can reconstruct it. And then the second one is then linking those to processes. And we can do that quite easily in basaltic melting systems. In other systems,
slightly more difficult with a granulite grade garnet.
Definitely.
Yeah.
Cool. Okay. Well, I'll have a play, and I'll probably get back to you quite soon. Thank you.
I just add another thing. I was talking with someone about this earlier today, which would be at your night. And they asked me, well, how is this different from things like PCA? Because you take your huge data set and you plot it into numbers. And my answer was, and it still is, that PCA changes depending on your data set. So, it's someone I was talking to about the carbonatites, which is my favorite thing in the world. And we're talking, well, if you take and apply PCA analysis to carbonatites, let's say from East Africa, and then you do it for carbonatites from China, you will have different principal components. They will not be the same. Okay, lambdas are the same everywhere, no matter what, as long as you normalize them to the same thing, which I use the O'Neill 2016 numbers. So they're always the same. The other thing is that the principal components themselves are they're kind of meaningless. Like you end up having, here's my component is 10 lanthanum minus 5 titanium plus 7 barium, whatever. It's very hard to get some kind of significant meaning out of this. Yeah. With lambdas, it's very clear. It is a shape. It's a parabola, it's a cubic, whatever. So that's something that you can intuitively say, this is what it means. And if you don't remember what each lambda means, you go on the app, you type in the number, and then you see it. The other thing is that PCA is a statistical method developed to maximize variance. Okay. And that may not be the thing that you want, because it will show you what things are different. Whether those things are petrologically or geologically important, that's a different question. Okay. And there may be things that aren't that variable, but they are important, and you will see that with lambdas. So that's a bit about PCA, and you can also use a PCA. I mean, you can have a plot of a principal component 1 versus lambda 4, and maybe you will see some. That's fine. I don't know. Go for it.
My argument would be add lambdas to your PCA analysis. So take the things which are not very highly correlated. So your other trace elements and maybe even your major oxides, calculate your lambdas on top of that, leave out the rare earth data, which is correlated, and then do PCA. And that's effective.
Yeah, that is
true. Can you do PCA in Pyrolite?
Well, you just link it to scikit-learn.
Okay.
Oh, okay.
I don't use it. So
It's two
I-
lines
I-
with scikit-learn.
Yeah.
And you just link it together, which is the nice part.
Okay.
Yeah. I think, Casper, do you have your hand up? Maybe. Well, if you do, butt in. Or it might be a legacy hand up. I'm not sure. I had a question. Oh yeah.
Hello.
Oh, hello, Casper.
Can you hear me? Can you hear me?
We can,
Yes.
yeah.
Okay. Your colleague was talking about carbonatites.
Mm-hmm.
In terms of normalization, I have also worked with carbonatite data. And one thing I noticed is that, for instance, now, if you bring a sample from China, if you bring a sample from, Namibia and other parts and plot it,
Mm-hmm.
there are three types of variation you observe. The first variation you observe is those ones that have high enrichment in light rare earth elements.
Mm-hmm.
And second type of variation you observe are those ones that have, high enrichment in heavy rare earth elements in comparison to light rare earth element fractionation.
Mm-hmm.
Another type you observe are those ones that tend to be average in terms of concentration, which tend to be comparable with that of alkali earth metals. Alkali, what's it called? Alkali igneous rock deposit or peralkaline igneous,
Yeah.
ore.
Yeah.
So I think there is no standard you can use to differentiate, rare earth element in different ore deposits. They tend to, display one kind of anomaly in different instances. Even when you go to regolites, like what I was also observed is that some people mistaking, buzite, laterite, and carbonatite, for ion absorption or deposits.
Mm-hmm.
There's a lot of misconception the way people see rare earth element in different ore deposits. Many of the classification I've seen and many articles I've seen, they tend to, compress everything together. And at the end of the day, they end up confusing themselves. Just like in terms of sedimentary ore deposits. In sedimentary, you have like phosphorite, you have, alluvial, marine and others. So some articles also tend to compress it and end up confusing themselves. And even though if you end up differentiating it, at the end of the day, the chondrite, the pattern you get will vary. It will vary. Like sometimes it is hard for you to differentiate regolite, associated carbonatite ore deposit. It's hard for you to differentiate it from carbonatite itself. Some people will say, like for instance now, I was reading an article that said that there's nothing like ion absorption ore deposit. Yeah, that there's no evidence to show, that the mineral concentration, that is the mineral, that's the saprolite, where there tends to be, high rare earth elements, enrichment in ion absorption or deposit due to, high weathering condition or, strong weathering condition. So they say there's no evidence that, such kind of, ore deposits exist. So
I would disagree with those people, but okay. I think ion absorptions exist, but yeah. I think though that maybe Michael's technique of plotting the lambdas of those might be a really good way of kind of testing that though. I also work in carbonatites and alkaline igneous rocks, and I do compile quite a lot of rare earth data, and I think you can sometimes pull them apart based on just chondrite normalized data. I think it also, you have to think about phases, what mineral phases you actually have in your rock and how the rare earths are partitioning to those, or if you have alteration, or you may have lost some of your rare earths if you've had fluids coming through. So I think you're right, you absolutely have to take the geological process into consideration when you are comparing those plots. But what I would now want to do is take that kind of data and apply all my lambdas, or not my lambdas, the lambdas, to it and see what it looks like. And I think that will be a really interesting take on it.
I just added something on carbonatite. So, that's the thing I spend most of my time on, especially with
The best
experimental
rock, let's
methods.
be honest.
Yeah, it's
I
the best
have,
one.
I have more than
Why would
100
anyone think of
data
any other rock?
locations.
Yeah, so the thing is that some of the things I'm seeing in the experiments that very often carbonatites will evolve towards a very similar compositions. So there's something there is a thermodynamic reason why a lot of carbonatites just end up looking very similar in terms of their earth elements, but it's not identical. So when you plot it on a earth element pattern, when you have a log scale covering 5 orders of magnitude, in those cases, it's very hard to see any differences. It's like when I showed the diagram with the zircon anomaly, right? If you do it with the linear interpolation, if you did it with the curve, it looked almost identical, but there was 20% difference. So I think what you said was that to take all of your data and just plot it as lambdas, what happens? You might find that you don't see anything. I think what's more likely that you will see something.
Like in carbonatite now, based on your method now, if I use your method and plot it, someplace, for instance, now I will get conventional carbonatite in the sense that there will be high light element fractionalization over heavy rare earth element fractionalization. Some place it tend to be flat, understand? Some place in some locations it tend to be flat, and in why some locations you tend to get a heavy rare element fractionalization, fractionating over that of light rare element. There's high concentration of heavy rare element over light rare element. So the pattern differs. For instance, in China, in Halopu, that is southern China, there's a carbonatite there.
Yeah.
And in Namibia also, we have, Bougainville. I think there's also a carbonatite there.
Yeah.
Those ones tend to display high heavy rare element fractionalization over light rare element fractionation. But in other locations, such as in what's it called, such as in Australia, that is mountain pass in US and other locations. I think those ones tend to display light rare element fractionalization over heavy. Why also in some location you get a flat, chondrite pattern. You get a flat chondrite pattern. And I think where the difference is more pronounced is in phosphorus or deposit. And that's why I was, asking a question on that for you to throw more light so that, I will know, what actually is happening.
How you would compare phosphorites with carbonatites and alkali igneous rocks. Michael, have you much experience in phosphorites? I only know a little bit about them. They tend to be light rare earth enriched, right?
They can be anything.
Can be, I guess.
Depending on where you are in the world, you can have some that are light earth element enriched, middle
I've only
enriched.
seen the stuff from Hungary. Yeah, I've only seen stuff from Hungary, and that's quite light rare earth enriched.
And I have a good friend who's working on phosphorites now as part of his job, and he shows me stuff, and you can pretty much find anything. Any kind of pattern that you want exists in phosphorites somewhere in the world. So
also,
it's,
metamorphic, I think,
it changes.
Also, metamorphic. So it tends to be a function of protolite.
Oh, so, hang on, Casper, you've just broken up for me. Casper, if you can hear me, sorry. Michael, can you hear him? I can't hear anything.
No.
Oh, sorry, Casper, I can't hear you. Could you write your question in the text? Sorry, I think we've just lost signal a bit.
I think it will be better. I will forward my questions because there's a lot of
detail.
Yeah, maybe also with some data to prove it.
Perfect. Great. Michael, you can have a whole pile of data to play with. I just had a look there in the questions. There's a couple of questions coming in for you there, Morgan, but I think you might already have answered some. Yes, Python is free, and then you can absolutely add Paralite packages for free. Oh, yes. Okay. Any differences between Paralite packages and other packages that are available? I guess your matplotlibs and your etc.
So Paralite builds upon matplotlib, NumPy, scikit-learn, and is designed such that you can pass the parameters and anything that Pyrolight's not using itself will forward on to say matplotlib. If you want to change the color of the plot and things like that.
Yeah.
In terms of other Python packages for geochemical stuff, there's not a lot out there. There's a few sort of graphical user interface based ones, which are right. But yeah, otherwise there's not a lot out there at the moment.
No, there isn't, which is why your stuff is great. I think, just in case you're interested, we've had participants from 27 countries today. That's pretty amazing. So that's why pandemic is rubbish. But I have to say, having these sort of virtual meetings and being able to catch up with people from across the world and, you know, hear researchers in Australia, you know, easily, it's fantastic.